Welcome back to another session of reading an article. This article title is Electronically Tuned Fractional Order Temporal Differentiator in Silicon Photonics. So this is a temporal order, fractional order temporal differentiator. There is a circuit called differentiator that is temporal nature, and it is fractional order. So the entire differentiator is electrically tuned on silicon in silicon photonics. So let us see the abstract. Here, full wave analysis and design of an electrically tunable optical fractional order temporal differentiator (DIFF) based on an ultra-compact micro-ring resonator has been presented. Electrical tunability has been realized through free carrier dispersion effect in the resonator with PIN and PN junctions. The first order optical DIFF is realized based on electrically coupled resonator without applying any bias voltage in the junction. Also, fractional order DIFF with differentiation order alpha is greater than 1 is realized by overcoupled resonator with the forward biased PIN and PN junctions. While fractional order diff with alpha is less than 1 is realized by undercoupled resonator with reverse biased PN junction. The high performance of the design tunable optical DIFFs and their high accuracy have been confirmed considering an ultra-fast Gaussian input pulse with short full width at about half maximum of 6.3 picosecond. Introduction. Optical computing based on integrated silicon photonics realizes ultra high speed and ultra low wide band optical processors such as optical DIFFs. This, let me say DIFF, this differentiator is the optical differentiator, integrator, and logic units with compact size and low power consumption. The fractional order differentiator expands the order of classical differentiator from an integer number to an arbitrary real number. It can be used for description of the compact dynamic systems behavior in micro and nano scales. Some of its applications in engineering are pulse characterization, ultra-fast signal generation, differential equation solving, ultra-high-speed coding, fluid flow, automatic control, biomedicine, image processing, signal processing, and signature verification. In photonics, the temporal differentiator is the essential processing block to calculate real-time temporal differentiation of the complex envelope of an arbitrary input optical pulse. Directional coupler, fiber brick gating, Manhattan interferometers, multimode interferometers coupler, and on-chip micro-ring resonator have been proposed to realize all optical temporal differentiator. Reference number 1 7 to 11. Among these structures, on-chip RRA is a good candidate because of its compactness, maturity in fabrication, and optoelectronic integration. For example, in CMOS technology. On the other hand, design of a tunable fractional order temporal diff is an important challenge in silicon photonics to realize desirable differentiation order. In reference 7, a polarizer has been used in the input of MMI coupler to design the tunable fractional order differentiator. However, this method is not suitable for circular polarization, and the proposed structure has large dimensions because of the large size of MMI coupler and its need to the polarizer. Therefore, the feasibility of designing the tunable fractional order temporal diff based on chip MRR should be investigated. There are common mechanisms to tune the resonance frequencies of MRR, such as the electro-optic effects, thermo-optic effect, and CFDs. It has been shown that electro-optic effect, such as linear electro-optic, that is focal effect, French-Keldysh effect, and Kerr effect, is weak in pure silicon. At that time, computation wavelengths of 1.3 and 1.5 micrometer. Also, TOE, that is thermo-optic effect, is too slow for the high frequencies required by telecommunication application. In fact, it can be used up to 1 GHz modulation frequencies. Therefore, CFD, FCD effect is the only solution to modulate refractive index of the silicon at the wavelength of 1.3 and 1.55 micrometer. It is related to the variation in the concentration of free carriers in silicon altering both the real and imaginary part of the refractive index. This is what is called carrier plasma dispersion effect. Okay. FCD can be realized in a silicon waveguide applying a voltage across its junction. Schottky PN and PIN junction, metal oxide semiconductor, and silicon insulator, silicon capacitor are common semiconductor junction to achieve modulation of the free carrier density. Typically, PN junctions are operated in either the forward bias mode carrier junction or reverse bias mode, that is depletion. While PIN junction can be operated in forward bias mode. Variations of carrier concentration in the forward and reverse bias PIN and PN junction lead to change in the effective refractive index. Consequently, MRR resonance frequency changes, which leads to change in the differentiation order. As a result, continuously tunable fractional order DIF can be realized by the tunable forward and reverse biased PN and PIN junction. In the previous work, to realize the tunable fractional order DIF based on RR, only a forward biased electrically tuned PIN junction has been used. Also, it is based on relatively large MRR radius of 30 micrometer and temporal full width at half meter of its applied optical pulses 30 picosecond. In our previous paper, the fractional order temporal differentiator based on ultra-compact optical MRR have been proposed, which can be used for ultra-fast signal processing. In this paper, for the first time, to the best of our knowledge, an accurate full wave analysis and design has been presented for the tunable fractional order based on the ultra-compact optical MRR with very small radius of 4 micrometer. Our calculations and the simulations are based on the powerful numerical and three-dimensional finite difference time domain technique and finite element method. FCD effect induced by the PIN and PN junction has been used to realize the continuous tunability in the designed fractional order differentiator. Intensity transmission and phase response of MRR based on PIN and PN junctions have been realized in the forward and reverse biases. Also, an ultra-fast Gaussian input pulse with a shorter full width half meter of 6.3 picosecond has been launched into the temporal DIF. At last, output of MRR-based DIF differentiator and the mathematical differentiator have been compared. So here, mathematical modeling. The alpha order fractional derivation of FT is represented by D, T, and FT. Where alpha is a positive real number. Its Fourier transform is Fourier transform of D, T. FT is a function, and we are taking alpha order fractional derivation. So derivation is I omega of L f of omega. Here omega and f of omega represent the angular frequency of the input signal and Fourier transform of FT respectively. According to equation 1, the transfer function of the mathematical fractional order differentiator as an optical filter can be written as 1, 2, 4, 7, 8, 22 as fractional order of this equation. First order differentiator. So H alpha equal to I to pi f. This fractional order is equal to this mode of 2 pi f. Fractional order exponential I alpha pi by 2. When f is greater than 1, and when f is less than 1 or less than 1 value is or greater than value is. Here f is equal to omega minus omega naught divided by 2 pi is the base band frequency and omega naught is the resonance frequency. Therefore, an alpha order temporal differentiator has an amplitude response of this omega minus omega naught power alpha and phase response of plus minus alpha times pi by 2. Photonic microwave resonator. So next meeting we will read the section 2.2 onwards. Thank you for attending this session.